So the kernel basically uses what is called a syscall handler, and a syscall handler is basically an interrupt handler. It's an exception handler for the system call. User space, the way that user space applications basically tell the kernel that they are in need of a system call is that they trigger an exception by, I mean, this is the way it works in reality. And the exception switches to kernel mode, switches that from user mode to kernel mode because it's an exception. It's sort of an interrupt basically, and then as we talked about in the second lecture, there are exception handlers, and the syscall manager or the kernel basically treats this as a software interrupt and basically starts running the system call the exception handler, which we talked about in the second lecture. This is pretty architecture dependent because the exceptions, the exception handler, as we said, for these interrupts are mostly hardware defined and hardware implemented. I'm not going to go into this little detail, but there are basically places, I mean, where you need to implement this in actually assembly to get the correct system call number. And then you have a function that is called system call void that takes anything that doesn't take anything as a parameter, and you do not need to worry about it, but this is basically how the mechanism works. Again, let's continue with how the mechanism is. You check basically the validity of I mean, once you're done with the architecture specific stuff, is that a system call, or is that, I mean, is that exception due to some hardware interrupt, or is that exception due to the user space trying to call a system call? Now you know that you're in the system call, then the system call function basically compares the system call number to the table to basically check if that system call that you're trying to call exists. If it doesn't exist, basically due to the numbers, you cannot find the number in the system call table, then you basically say that it does not exist and call the LinuxSysCalls file. Otherwise, you basically start the system call that you have just found in your system call table. And then there are details on how the memory is referenced for that. So each element in the system call table is 64 bits, and that basically means that the kernel multiplies the given system call number by 4 to arrive to the right location in the system call table, and this is just for x86. This is very x86 specific. Okay, and the actual implementation has actually nothing to do with the mechanism. So what the past two slides were basically how the flow goes from the user space to kernel space, and including how it deals with the hardware interrupts. Okay, or the software interrupts using the hardware. But the actual implementation has nothing to do with the mechanisms. There are a few rules of thumb when you start implementing a new system call. First one is that you try to never multiplex system calls. So you should not have a get PID one process, which basically, well, a system define get PID and then have one, where you basically say that this system call, if it gets as input number 1, then it will return the thread ID. If it gets an input number 2, then it will return the process ID. If it gets 3, then it returns the parent's ID. I mean, this is very frowned upon. You should not have the input to the system call controlling the output of the system call. If it's worth it, then just implement a new system call. Okay, if it's something that people will feel towards, then we implement it newly. So it could have been that, for example, in the get PID system call, we saw that there's a get PID and there's get TID system calls that sort of one of them returns the process name and the process number, the process, sorry, the thread group ID, and the other returns the thread ID. You could have implemented them in one and basically multiplexed on the parameter, but that is bad. Okay, think about it as you need clean and simple interfaces, because this is something that people will use and need to understand. So if you make it, the more complex you're going to make it, the much worse that experience of programmers will be when using it, of system level programmers. Okay, and you want it with the smallest number of arguments possible. Actually, there is a limit on the number of arguments, and if you go beyond that, then you will need to actually reference memory in the stack to basically say that, okay, these are the more arguments. And I think the limit for x86 is like 6 arguments. It's either 5 or 6 arguments, and if you have more than that, then you just go and start reading memory and start understanding arguments yourself. So keep your arguments as minimal as possible. You should think that an interface, a syscall interface, will not be something that is used today, but something that will actually live with Linux for the next 10 years. So that's for general syscalls. That's not for your assignment, though. Your assignment is something that will die after the course, maybe live on your GitHub accounts. So design it to be as general as possible. So if you can design your syscall to be usable for different architectures, that's super. If it's not architecture dependent, or if there is a way to make it not architecture dependent, such that it does not hurt performance a lot, then it's a good thing to do. You should not also make or you should try to reduce assumptions on the architecture's word size, basically how many bits is your processor, and its NDNS. And well, you probably forgot about what NDNS is, but you can look it up at Wikipedia. It's one of these things that people keep forgetting about. But the reason for that is that, well, you have an ARM architecture that was basically 32-bit, and now there is a 64-bit architecture out of ARM, and you can actually, from processor to processor, from basically family to family, in the same processor architecture, so ARM64, change NDNS. And well, this is not nice, but it is actually true. And there is a very interesting Linux philosophy that you need to keep in mind, is that you are providing mechanisms, not policy. You provide ways, but you do not tell people how to do things.